I'll just announce. Okay, so, well, welcome everyone to a new session of our category seminar. So today we have the pleasure and the honor of having Emily Riehl with us. She'll be talking about her work on infinity cosmoi. Yeah, just before starting, if anyone wishes to ask a question during the talk, please unmute yourself or ask the question in the chat. In that case, I can ask the question for you. If any of you doesn't feel comfortable asking your questions in English, please ask the question in Spanish, and I'd be very happy to translate for Emily. So students are especially encouraged to ask questions. So yeah, please, Emily, take it away. Thank you very much.
Great, thanks. It's a pleasure to be here. Firstly, I have a version of the slides on the web, so I'll drop that in the chat if you want to follow along at home. And now I guess I'll share. I'm not allowed to share, so I guess I need permission.
Yeah, okay, maybe Carlos, can you make Emily a co-host?
Make me a host, for instance, or whatever is easiest. Yeah. Great. So now I have all the power. Okay. Great. Does this look all right? Cool. Okay, so let's give it a go. So thanks very much. I'm very happy to be here. So today I'm going to tell you about some joint work with a close colleague of mine, Dominic Verity from Macquarie University in Sydney. And really what I'm doing is I'm advertising a book that's actually just come out. In fact, I got my own copies yesterday, so I finally have a physical one. I guess there we go. So it's a new book on infinity category theory. So it's a sort of a new perspective on the foundations of infinity category theory. So I'll explain in a bit. By infinity categories, I mean infinity one categories. This book, by the way, is also free on the web. So if you want to have a look at it yourself, you don't have to buy it, which I'm very grateful for the publisher for letting us do that. So I'll drop a link to that in the chat as well, once I can find. Of course, once you've started sharing your screen, you can't see the chat anymore, but there it is. Okay, maybe I can't actually see this right now. Oh, there it is. Okay, so, but let me start by explaining kind of what on earth I'm talking about. So, right, so what are infinity categories and what are they for? So Barry Mazur has this really lovely metaphor that he uses to explain categories. So he says the category frames a possible template for a mathematical theory. The theory should have nouns and verbs, i.e. the objects and the morphisms, and there should be an explicit notion of composition relating the morphisms. The theory should, in brief, be packaged by a category. So this was in a tribute to Saunders MacLean. So a way I think about what an infinity category is as, the objects that mathematicians study become richer. Sorry, ordinary categories do a wonderful job of framing the sort of mathematical objects that were sort of central to 20th century mathematics. So, Emmy Noether took this point of view that to study groups, those are the nouns in group theory. You should also study group homomorphisms. Those are the verbs in group theory. But if a group is now some sort of higher group, some sort of higher dimensional object or something like a chain complex, then the theory just needs a little bit more structure. So adjectives, adverbs, pronouns, prepositions, conjunctions, interjections. So that's my metaphor for what an infinity category is. It's going to allow you to be a little bit more refined in how you study some sort of object. So like an ordinary category, an infinity category has objects and morphisms between them. You can think of the objects as being zero-dimensional somehow, and the morphism you would draw as a one-dimensional thing. I'm calling it a one morphism because what's new in an infinity category is this higher dimensional structure. So in an ordinary category, if I had a morphism F that points from something X to something Y and a morphism G that points from something Y to something Z, then there would be a specified composite morphism from X to Z. In an infinity category, by contrast, you think of composition not as an operation, not as a function anymore, but as something that is witnessed by some higher dimensional invertible morphism. So I would say that an arrow here, this thing that I've written, G composed F, is not the composite of G and F, but rather a composite of G and F when there exists an invertible two-dimensional morphism alpha that's filling this triangle. And this alpha is really a bit of data. It's not just a condition. So I've given it a name. So that's a different perspective on composition. And we're used to, we'll see an example on the next slide. And then there's a different perspective on associativity also in an infinity category. So in an ordinary category, the composition is an associative operation, just meaning that H composed G composed F is H composed G composed F, where you should have put some brackets in those expressions. So in an infinity category, you know, I would choose a composite of F and G, that's this arrow G composed F, together with this witnessing invertible two-dimensional arrow alpha. Then I could choose a composite H composed G of G and H together with its witnessing two-dimensional arrow beta. And then I could choose a composite of F and H composed G. That's this arrow on the top together with its witnessing two-dimensional arrow gamma. And then I can compose together those three two-dimensional arrows to obtain a two-dimensional arrow that inhabits this back triangle. And that thing is then a witness that this H composed G composed F is also a composite of G composed F with H. So that's a proof of the associativity property, though even that perspective is actually slightly incorrect, because you might imagine having already chosen a two-dimensional, invertible two-dimensional arrow inhabiting the back triangle. And then associativity is really itself data rather than a property, namely of an invertible three-dimensional morphism that would then fill inside the tetrahedron that I've just defined. And this story doesn't stop here. So these witnesses need to be coherent up to invertible morphisms all the way up. And also this alpha, beta, gamma business, these are arrows in their own right. So they need to be composable in the same sense that the one-dimensional arrows are, that is up to an invertible morphism in the higher dimension, and so on and so forth. So an infinity category is really a pretty complicated sort of structure. So let me give an example that illustrates kind of why all this complexity is needed. So so the full homotopy type of a topological space. So imagine your favorite topological space. Here I've drawn some like genus 3 thing, is captured by its fundamental infinity groupoid. So this is closely related to the fundamental groupoid, if you've seen that, or even the fundamental group. But that really captures the low dimensional information in a space. This is something that's going to capture the high dimensional information also. That's why I'm saying the full homotopy type. So objects here are the points in your space. So this is a huge, huge thing. Each point is an object. Each one morphism is a path. So each path defines a one morphism. And I'm not taking homotopy classes of anything. I'm just saying the paths themselves are one morphisms. Now, if you think about how paths compose, I mean, path composition is a little bit delicate. I mean, you can sort of concatenate one path with another path, but then there's the question of how you would parameterize that. And it's known that there's no sort of strictly associative way to parameterize that. So here again, we take this sort of different point of view. So any composite of the path that goes from this point to this point, and the path that goes from this point to this point. So any path that goes from the start to the end and is homotopic to, meaning you can fill in the triangle with a two-dimensional path, is regarded as a composite. So these two morphisms are these homotopies between paths. These three morphisms are the homotopies between homotopies, and so on and so forth. So in an algebraic sense, this structure is kind of quite complicated, but in a geometric sense, it's actually pretty natural. We're just collecting together the data of the points and the paths between paths. Sorry, that's what a homotopy is. It's just a path between paths. And a homotopy of homotopies is a path between paths, and you have paths between paths between paths between paths, and so on. So we're mapping from intervals and cubes, or squares and cubes and hypercubes and so on into your space. Okay, so the quotient, so this infinity groupoid is just all of this data together with all the composition structure. Now there's a quotient of this that is an ordinary category, so just with objects and morphisms and strict composition and all that. And that is the fundamental groupoid of points and based homotopy classes of paths. So this infinity category, this fundamental infinity groupoid could be thought of as some enhancement of the ordinary fundamental groupoid. It has all of the information of that, but then it has all this higher dimensional stuff going on as well. And that's actually quite common for the relationship between infinity categories and ordinary categories. So there's something called the derived category of a ring, which you may encounter at some point. That's the homotopy category of an infinity category called the infinity category of chain complexes, which would keep together chain complexes and chain morphisms, but then also chain homotopies and higher degree maps as well. And similarly, there's something that comes up in quantum field theory. It's a category of closed end manifolds and diffeomorphism classes of cobordisms. And that can be understood as a homotopy category of some infinity category of closed end manifolds and cobordisms. And then you collect on top of that the additional data of the diffeomorphisms and then isotopies between these and so on and so forth. So here and throughout the talk, I'm using infinity category as a nickname. So Jacob Lurie introduced this nickname for the n=1 special case of an infinity n category. And what that refers to is it's a weak infinite dimensional category in which all morphisms above dimension n are invertible. So in particular, in this talk, in our infinity categories, we have objects and one-dimensional morphisms, and the only higher morphisms we'll discuss are invertible. So there's invertible 2 morphisms, invertible 3 morphisms, and so on, but we don't have any non-invertible data in higher dimensions. That simplifies things considerably and will be useful today. Okay, so that's meant to be kind of a quick high-level overview about what infinity categories are, what they're for, where they come up in mathematics, but there's some things that are pretty strange about the way infinity category theory is presented that I want to draw explicit attention to. So I'll call these curiosities. So Carlos Simpson, for just to give a very explicit example, gave a beautiful introduction to infinity called infinity categories and why they are useful. This was in a workshop on derived algebraic geometry and birational geometry and moduli spaces at MSRI. And I've written the abstract here in case you're curious about why infinity categories are useful. But what was interesting about his talks, and again, they're really beautifully done. I highly recommend watching the videos, is that, this is a 3-hour introduction to infinity categories, and yet somehow the definition of an infinity category doesn't appear into the second half of the talk. I mean, this is the second half of the second talk even. So like an hour and a half in, we finally get a definition. I mean, this is completely unlike how most math lectures go. You define the thing right away because mathematicians, we like very precise definitions, and then you start proving all these theorems about it. But somehow with infinity categories, that's not often. This definition is delayed. And again, I'm not picking on Carlos. These are beautiful lectures. I totally understand why he did it the way he did, but it's a little bit curious. So another curiosity is that if you watch the first hour and a half of his lecture series so that you can finally see the definition of an infinity category, you might notice that it's a different definition that appears elsewhere in the literature. So the definition of infinity categories that he gives in that series appears in a famous paper of his with Andrei Hirschowitz. But there's a different definition that would appear in a paper of Borbida de Brito and Michael Weiss on spaces of smooth embeddings and configuration categories. And yet another definition appears in this famous paper on algebraic K-theory. And still another definition is used at various points in higher topos theory. So that's also a little bit strange, is that we have these completely different definitions of what an infinity category is. In the community, these different definitions are referred to as models of infinity categories. This is not a model in the sense of model theory. So if you're familiar with that, I apologize, but this is kind of the best word that we have. So I'm implicitly referring to 4 models here, namely the Siegel categories model, the complete Siegel spaces model, the quasi-categories model, and something that I would call one-completial sets, you might know of as marked simplicial sets. So these are different models of infinity categories. And what these models are is, if you want to give a precise definition of a mathematical object in the traditional foundations of mathematics, the traditional foundations are based on set theory. So when you kind of boil it all the way down, most mathematical objects are sets with a whole bunch of structure. And that's what these models are as well. So the first one is a bisimplicial set, as some sort of set with a whole bunch of structure, discrete objects. The other one is also some sort of bisimplicial set. Third one is some sort of simplicial set. The fourth one is some sort of marked simplicial set. So these are all sets with structure. These are precise definitions. Bourbaki would recognize them as mathematical definitions, and now we're ready to do mathematics. Okay. But so what the models do for infinity category theory is they give a precise definition. So this wishy-washy thing that I gave at the beginning, this is not a definition. I mean, this is a sketch of what the idea of an infinity category is, but it's not at all a definition. And the models actually are. They're definitions that, you know, a mathematician would recognize as a definition of something. But, you know, there's something a little bit unfortunate about them in that they're different. You know, they're not all the same. And this causes a problem, or at least a headache. I don't, whether it's a problem is, I guess, a matter of debate, but it certainly causes a headache. So a lot of work has been done. You know, once you know what an infinity category is, you want to be able to extend ordinary category theory to infinity category theory. So, you know, once you've started learning about categories, you learn about equivalences of categories and adjunctions between categories and limits and colimits in categories and the innate lemma and monads and whatever. And you want to have all of that for infinity categories as well. And so a lot of work has been done, you know, starting by Riehl and then continued by Jacob Lurie in proving these fundamental results, but then sometimes, you know, to prove it precisely in a way that Bourbaki would recognize as a proof, you know, it's common to pick a particular model. The quasi-categories model in particular is one that's very commonly chosen. But then sometimes this work is later redeveloped starting from a different model. So an example, here's a very nice paper that describes the problem explicitly. So in the introduction, it says, in recent years, infinity categories appear in various areas of mathematics. In his books, Lurie develops a theory of infinity categories in the language of quasi-categories. So that's, again, one of the particular models, and extends many results of ordinary category theory to the setting. In his work, Resk introduced another model of infinity categories, what he called complete Seidel spaces. This is one of these other models. It has certain advantages. Now, it's natural to extend the results of ordinary category theory to the setting of complete Seidel spaces. In this note, we do this for the innate lemma. So certainly it is natural to do so. But again, this is a little bit distressing because if you know how hard it was to prove these theorems in one model, it's a little bit annoying to think that you're going to have to prove them all again in a different model to be able to use them there. And maybe a final curiosity is that if you attend enough talks about infinity categories, you'll often note that the experts in the area prefer to avoid using a model at all. And in fact, Jacob Lurie in the preprint that became the book Higher Topos Theory, which is kind of the foundational text in the area, wrote, we will begin with an informal review of the theory of infinity categories. This is a joke because the theory of infinity categories didn't really exist when he was writing this, but there are many approaches to the foundations of the subject, each having its own particular merits and demerits. Rather than single out one of these foundations here, we shall attempt to explain the ideas involved and how to work with them. The hope then is that this will render this paper readable to a wider audience, while experts will be able to fill in the details missing from our exposition in whichever framework, i.e. in whatever model they happen to prefer. So, somehow these models are kind of beside the point. Like they're choosing these coordinate systems that, people working in the field really just wish they weren't there. I mean, an infinity category is somehow a more fundamental notion than any of the models are. And yet it seems that we're forced to work with these models to rigorously develop the theory of infinity categories. This is something that everybody hates. So this is all meant to describe kind of what we do in our book project. So a main theme from this new book, Elements of Infinity Category Theory, is that the theory of infinity categories can actually be developed, or at least a large fraction of it can be developed in a natively model independent fashion. So this is going to be a new strategy for proving for giving definitions in infinity category theory, so defining limits and colimits and adjunctions and all of that, and also for proving theorems about infinity categories. So this will be a new strategy for both of those things that does not rely on the models in the same way that the old strategies did. So how do we do this? So we developed the theory in this axiomatic setting that we call an infinity cosmos. So an infinity cosmos is it's the universe in which the infinity categories live as objects. We give some axioms for an infinity cosmos, and then we prove all of our theorems from those axioms. And because each of the models that I've mentioned defines an infinity cosmos, then all you have to do is specialize these general theorems about infinity cosmoi to any of the particular settings, and now you have the theorem in the model that you prefer. So essentially, we're just using abstraction, or maybe the philosophy of category theory applied to infinity category theory to kind of redevelop the foundations. So another advantage of this kind of point of view, where we're sort of zooming way out and now thinking about the categories in which infinity categories themselves live as objects, is it really allows us to think rigorously about what happens when we change models. So, part of the reason is that there are so many different models of infinity categories in the literature is they do have different advantages. Certain examples of infinity categories arise most naturally in one model or the other. So it'd be nice if you can kind of transfer information back and forth between them. And so one of the things we show is that there are these certain change of model functors that define what we call biequivalences of infinity cosmoi, which preserve, reflect, and create infinity categorical structures. So what that means in particular is you could construct a functor between infinity categories in one model and then pass to a different model and then construct its adjoint, for instance. That's the sort of thing that this will allow. We show furthermore that not only that theorems about infinity category theory that are proven both synthetically, that is kind of in a model independent fashion, and also analytically, that is using the combinatorics or the techniques of a very particular model, the conclusions of those theorems transfer between models. So even if your proof is particular to the quasi-categories model, for instance, as long as the result that you've proven is, it can be stated in a precise way that we make precise and in a particular formal language, then the conclusion is true in the other model, even though the proof would not be able to transfer there. Okay, so that's kind of the high level summary, but maybe I'll stop and see if there are any questions before continuing.
Yeah, no, it doesn't seem like there are any.
Okay, let's carry on. So here's the plan for the rest of the talk. So I'm going to give a small take. I mean, this is a long story and was, something we've been working on for a decade maybe, but I'm going to give you a small taste, firstly, of what formal category theory is like, how you could prove a theorem in category theory without, giving a precise definition of an infinity category. Then I'm going to explain how these model independent foundations work. And then if there's time at the end, I'll also discuss how the proof of the model independence goes. Okay, so I guess to warm up into formal category theory, let's kind of review what category theory is and what it's for. So here's a theorem. It's not obviously categorical. So for natural numbers a, b, and c, a times b plus c is equal to a times b plus a times c. So here's my favorite proof of this theorem. So by categorification, I'm going to choose some sets, capital A, B, and C, whose cardinalities are these numbers. So, finite sets representing those cardinalities. And to prove the equation between cardinalities, I'm going to instead exhibit an isomorphism between sets, where I'm also categorifying their arithmetic operations. So this times, when I've written it in red, is the Cartesian product, and the plus, when I've written it in red, is the disjoint union. So these are operations on sets that have the intended effects on the cardinalities of those sets. So it's not so hard to just directly write down an isomorphism, even a natural isomorphism, but here's an even cleverer way to come about it. So by the innate lemma, rather than exhibit an explicit isomorphism between these sets, I'm instead going to define a natural bijection between the sets of functions whose domain in the one case is the Cartesian product of A with the disjoint union of B and C, and whose codomain is X, and then functions whose domain is the disjoint union of the Cartesian products of A and B and A and C, and whose codomain again is X. So by the innate lemma, if I have a natural isomorphism between these collections of functions, then I can conclude that there was an isomorphism between the domains. And that's the goal, again, because then I decategorify and have proven distributivity of times over plus. Okay, so how do we do that? So really the proof here is the proof that left adjoints preserve colimits. So I can imagine that I have a function whose domain is the Cartesian product of A with the disjoint union B and C and it valued in X. So by currying, that's transposing across the adjunction, this function of two variables can be thought of as a function of one variable out of the disjoint union B plus C and into the set of functions from A to X. That's what this exponential refers to. But now I have a function that's mapping out of a disjoint union by the universal property of that colimit. That's really just a pair of functions. So one from B into the set of functions and one from C into the set of functions. And now I can uncurry. So I'm transposing back across an adjunction here. And I have a pair of functions, again, of two variables, one from the Cartesian product of A and B into X and one from the Cartesian product of A and C into X. And then I could pair up those two functions again using the universal property of the coproduct, and I get a single function from the disjoint union of the Cartesian products into X. Okay, so that's a proof. So why did I do all that? So this the same argument that we went through at the very end, where we transposed some function, we applied a universal property, we transposed again, and then again applied the universal property. This proves this general theorem called left adjoints preserve colimits. And this theorem kind of comes up all over the time, place in mathematics, and the proof that I gave just then is a pretty nice one that works in all of these settings. So I'm going to ask my abstract algebra students next week to prove that there's a linear isomorphism of vector spaces involving the tensor product and the direct sum. In fact, somebody asked me in class today how the free group on a disjoint union of sets related to the free product of free groups. So that's an instance of this result. The right exactness of the tensor product. Here's my favorite example, actually. So if I have a function between sets A and B, then the inverse image function between the sets of subsets preserves both unions and intersections, while the direct image function only preserves unions. And the reason that the inverse, firstly, the reason that the direct image function preserves unions is that this can be understood as a left adjoint between poset categories, and left adjoints preserve colimits, in particular unions. The inverse image is the right adjoint, so it preserves intersections, but inverse image also has a further right adjoint. So being both a left and a right adjoint, it preserves both the unions and the intersections. This really mystified me as an undergraduate, and now I feel like I finally understand it. In this last example, I secretly appealed to something called the categorical principle of duality. So any theorem in category theory has at least one dual theorem where you just kind of turn all the arrows around. And the dual result for this left adjoints preserve colimits, or one of the dual results, is that right adjoints preserve limits. And that's actually what I'm going to focus on going forward. Okay, so I want to give you a proof that right adjoints preserve limits, a very, very formal proof of this. And so first I should give you a definition of what an adjoint is and what a limit is. So we'll do that. These definitions I expect to be completely unfamiliar even to the experts. Anyway, I'll do my best. So what is an adjunction? But they're equivalent to the standard one. So these are the same notions, it's just presented in a different perspective. So what is an adjunction? So it's given by the data of a pair of categories, A and B, a pair of functors. One of them should point one way and the other should point the other way. So U and F, because it's often underline and free, but whatever. And then there's a natural transformation. So a natural transformation is the name for a morphism between functors. So this A, B are categories, this U and F are functors. This natural transformation epsilon is a two-dimensional morphism whose source is the composite of U followed by F, and whose target is the identity functor on A. So I've drawn it in this triangle for a reason that I'll reveal, but again, what you should read this is a two-dimensional morphism whose source is U followed by F, and whose target is the identity at A. And for this triple of data, this U, this F, and this epsilon, to be an adjunction, this epsilon must have a universal property, which is called being an absolute right lifting. And what absolute right lifting means is the following. So if I'm given any natural transformation alpha, whose source is F of B, and whose target is A, I've arranged it in a square, but really this is a natural transformation from FB to A. But those are the names of functors, by the way. then that factors uniquely through epsilon in the way that's displayed by this pasting diagram. So this beta here is a natural transformation from B to U, A. I can whisker this beta with F and then compose it with epsilon whiskered with A, and that recovers alpha. So this is a definition as a unique factorization property. It's a little bit different, but one thing you should observe is this. So this alpha here, so to say that something factors uniquely, we're exhibiting a bijection between natural transformations alpha from FB to A and natural transformations beta from B to U of A. So this is something like the transposing universal property of an adjunction that might be a little bit more familiar. And this bijection is implemented by pasting with epsilon. That's the epsilon defines one of the transposing functions. Anyway, this is a way to express the notion of adjunction internally to the two category of categories, functors, and natural transformations. That's what you've achieved. So the reason I like this absolute right lifting diagram definition of an adjunction is I can define a limit on exactly the same footing. Again, this is not at all the traditional definition of a limit, but so the input to a limit is a diagram. So that's just a functor from J to A. And a limit of that diagram is given by, again, another one of these absolute right liftings. So the data here, so firstly, this one is the terminal category. And I've transposed to, rather than have my diagram be thought of as a functor from J to A, I'm thinking of it as an element that is a map from one into the category of functors from J to A. So D can equally be regarded encoded by this functor. Now the data of a limit is firstly, it's an object inside the category A. So that's this map from 1 into A. That's this little L is the name of an object inside A. And then it's a limit cone, which is a natural transformation from the constant J-shaped diagram at that object down to D. And that's what this lambda is it's the limit cone. Its domain is the constant functor applied to L. So the constant J-shaped diagram at L, and its codomain is D. So that's the usual data of a limit. And this is not its universal property, but it's equivalent to its usual universal property. So again, it's an absolute right lifting, which means that whenever I have a natural transformation that inhabits a square like this, it factors uniquely through lambda as follows. And you note these factorizations are exactly the same sort of shape. That's what absolute right lifting diagram means. So what's useful about these definitions is now I can give a sort of one-page proof that right adjoints preserve limits, and let's do it. So what's the statement firstly? So I should imagine that I have a limit so I have a diagram D as before, and I have a limit of it. So I have this absolute right lifting thing. This L is the limit object. This lambda is the limit cone. Now, if U is the name of a right adjoint functor, when I paste this together, so I form this diagram on the top, now I have along the bottom, I have the composite diagram U applied to D. So that's going to be my diagram in the category B now. And along the top, I have U applied to L and U applied to this cone lambda. So I have a new cone over a new diagram in B, and I'd like to argue that that's a limit cone. That's the statement that right adjoints, namely this U, preserve limits, namely my L and my lambda. So I want to show that this top thing is absolute right lifting. So I'm going to use a lemma, which I haven't proven, but if I had stated it, you'd be able to prove it yourself. So absolute right lifting diagrams compose and cancel on the bottom. So if I have two of these special triangles and I stick them together, I have another absolute right lifting diagram. And there's also a one-way cancellation property. So in other words, to show that this is absolute right lifting, I could paste on diagram on the bottom this co-unit epsilon of the adjunction. Since the co-unit is absolute right lifting, this cancellation result tells me this top thing is absolute right lifting if and only if this composite triangle is absolute right lifting. But now this diagram can be rearranged here. So I'm using, I guess, like the two naturality of the Cartesian closed structure on CAT or something like that. So this epsilon is just defined kind of component wise in terms of the co-unit of the original adjunction. And now this diagram rearranges as follows. This is an identity square, so I just cancel it. And now I have my original limit cone and my original co-unit. And again, those are two absolute right lifting diagrams and they compose. So I have an absolute right lifting diagram. Okay, so that proof went way too fast, of course, but what I'm trying to illustrate is sort of the style of the proof. So we're just using arguments inside of a two category. So why am I doing all of this? So I've just proven that right adjoints between ordinary categories preserve limits inside ordinary categories, but this is the proof that appears in our book, and proves that right adjoints between infinity categories preserve limits in infinity categories. So what I'm going to do now is explain how this actually also proves that. But let me stop for a second and see if anybody wants to interrupt me.
I have a question here.
Please.
So it seems to me that the first equality, you said that it cancels along the bottom. It's
Right. So by the first equality, did you mean? See if I can highlight. No. Did you mean the one on the left?
yes.
Great. Yeah. So what's equal here is you can ignore the lambda and the L bit and just look at the stuff involving A and B and U and epsilon. So this sort of pentagon is equal to this other pentagon. And the reasoning has to do with the fact that these maps delta, which I didn't really say too much about, these are the constant diagram functors. They define the components of a two natural transformation. So naturality means this top square involving U and UJ and the delta commutes. That's ordinary naturality. Two naturality says that if I stick on this epsilon to the J at the bottom, that's the same as having the epsilon on the top instead and the naturality square on the bottom. So there is something to check there, but it's
okay.
True. So
okay, it's that I couldn't follow that.
Oh, of course, it went way too fast. That's totally fine. So,
okay, thanks.
sure. Great. Okay, so let me try and explain how. So again, this was an argument that took place in the two category of categories, functors, and natural transformations. So it's surprising that it's relevant in any sense to infinity category theory, and I want to try and explain that now. Okay, so before I tell you about the model-independent foundations of infinity categories, I should tell you a little bit about how the models work. So, so the meaning of infinity category is made precise by several models connected by these change of model functors. So here I've explained a few of them, or not explained a few of them, listed a few of them. So the two kind of easiest to understand are called topological categories and relative categories. From the point of view of developing the theory of infinity categories, these aren't quite optimal though, because they have sort of the right objects. So any infinity category could be instantiated as a relative category, for instance, but the maps between them are a little bit too strict. So if I want to represent a functor between infinity categories as a map of relative categories, I might have to change the domain and the codomain. And so from the point of view of developing the category theory, that's kind of a pain. And so those models won't really be used. So the other four models, so these are the quasi-categories, RESC spaces, also known as complete Siegel spaces, Siegel categories, and one completional sets. These have the correct maps, and they're also kind of enriched over themselves. They each have an internal HOM. And so these will be the models that I'll refer to going forward that will admit into our world of model-independent infinity category theory. I should say while I'm here that if you're curious to learn more about models of infinity categories, Omar has a very wonderful expository whirlwind tour of all the models, and I highly recommend that. That mentions even more than I've mentioned here. Okay, so you might ask how you would develop the category theory of infinity categories, how you would sort of state and prove theorems about infinity categories, and there are two general strategies. So the traditional one I would describe as analytic. So this is just a metaphor, not a technical term, but we could give the categorical definitions and prove theorems using the combinatorics of one of the models. So take advantage of the fact that quasi-categories are simplicial sets, and then use stuff about simplicial sets to state definitions and prove theorems. That's a traditional approach to infinity category theory. But our strategy, by contrast, is to work synthetically. So we're going to give definitions that are expressed in a more abstract way, but then we'll apply to all of these models at once, all of the well-behaved ones at once. And then our theorems, we prove in an abstract setting that will specialize to theorems in each of these things. And how that works is we introduce this thing that we call an infinity cosmos. And it's an axiomatization of the common features of these categories. So again, this thing, quasi-category, rest space, complete single space, one completional set. These are names of things. An object in this category would be an infinity category in that particular model. But we're zoomed up a level. So we're going to think about the totality, the category of all quasi-categories, the category of all complete single spaces. Those are these things that are going to be infinity cosmoi. Okay, so in a different sort of talk, I would give a fully elaborated definition of an infinity cosmos. It's not so difficult. If you're familiar with some sort of abstract homotopy theory like Quillen's model categories, it's not so hard to make it all fully precise. It would take about a page. Here I'm going to be a little bit more impressionistic because we're not going to use the axioms for anything anyway. So, I'm not going to tell you entirely what they are. But the idea of an infinity cosmos is that it's an infinite dimensional category whose objects are infinity categories. That's how we're going to use it. Since as ordinary categories live most naturally in a 2 category, these infinity categories, which are infinity 1 categories, will live most naturally in an infinity 2 category. And the additional structure that is going to allow us to prove all our theorems is that this infinity 2 category has certain infinity 2 categorical limits. So, comma constructions in particular for the folks in the know. Okay, so what actually is the definition? So firstly, an infinity cosmos is just an ordinary category to start with. If you're familiar with the models, you would know about the category of complete single spaces and morphisms between them, for instance. So you start with an ordinary category. Then you want to equip that category with a particular simplicial enrichment. Often there are choices involved, so that's why I'm saying a particular one. So you give it a particular simplicial enrichment so that the Hom spaces in this case, the mapping spaces, are themselves quasi-categories. So that's a particular sort of simplicial set. And this step right now is how we're getting an infinity 2 category, by the way. We're using a very kind of unreasonably strict model of infinity 2 categories, so we don't have to appeal to, the as currently under development theory of infinity 2 categories. So an infinity cosmos is a category that's enriched over simplicial sets in such a way that the Homs are all quasi-categories, and we use this notation fun AB for them, because if you've read higher topos theory, then you'll be happy. It's the same notation Jacob uses for the same sort of thing in the infinity cosmos of quasi-categories. Okay, so then our 1 category again of objects and morphisms, we specify a certain class of morphisms and we call them isofibrations. The reason we call them isofibrations is there's a thing in ordinary category theory called isofibrations, and these are analogous to those. And these have familiar closure properties that you'd expect for fibration. So they're stable under pullback, they're stable under composition and inverse limit of Tower, and then there's some like pullback exponential business. So these are called isofibrations. They have kind of no fundamental meaning in a sense. Any morphism is equivalent to an isofibration, but they allow us to use very, very strict limits to model weak limits. This is kind of how fibrations are used a lot in model category theory, for instance, and we're doing exactly the same thing here. So then the final axiom, we ask that our infinity cosmos have some sort of limits. So we ask an infinity cosmos to have certain limits, namely pullbacks of isofibrations, products, cotensors with simplicial sets. That's maybe a slightly exotic one. And we ask these to be enriched limits. So they satisfy not only the usual 1 categorical universal property, but a simplicially enriched universal property. So these are very, very, very strict limits, but they model weaker limits because we're using isofibrations in our diagrams. And that's somehow the full definition. So what do you need to know about infinity cosmoi? We have a whole bunch of examples. So in particular, the intended examples are these models that I've been harping on about, but secretly there are a whole bunch of other models as well. And that's kind of an interesting aspect of the theory. So an infinity cosmos is not at all an axiomatization of a category of infinity 1 categories, because there are all of these kind of exotic examples as well. So for instance, there are various models, in fact, several models of infinity n categories define infinity cosmoi or assemble into infinity cosmoi. If you have an infinity cosmos K and you have an object in it B, you could slice over that and get an infinity cosmos. There's also an infinity cosmos of stable infinity categories and exact functors and a whole bunch of examples like that. So there are really quite a lot of these around. And what the axioms are for are sort of proving theorems and not for defining a fundamental notion that exists in the universe, I guess. The way we can kind of talk about infinity categories in both a rigorous way and an understandable way is as follows. So I'm going to use infinity category now as a technical term. So remember at the start of the talk, one of the things we were unhappy about is that I couldn't give you a definition of an infinity category. So now I'm going to give you a definition, though it's kind of a funny definition. So once you've defined this notion of infinity cosmos, this really is, I didn't fully elaborate it here, but this is a definition in the sense of ordinary mathematics. It's a set with a whole bunch of structure. So once you have an infinity cosmos, an infinity category for me is an object in there. So I'm using it as a technical term to refer to an object in an infinity cosmos. And similarly, infinity functor is a technical term to refer to a morphism in an infinity cosmos. So this is this one category that we started with in an infinity cosmos. The objects and morphisms are called infinity categories, infinity functors. And the reason for this is this will let us state our theorems in kind of a natural way. So I'm going to prove some theorems about the objects in an infinity cosmos, but I could call them theorems about infinity categories. And this makes sense, again, because in these examples, an infinity category is an infinity category. So it's a way of kind of reappropriating this term in a model-independent fashion and making it a little bit rigorous. Okay. So part of the reason that I didn't bother to give you a full definition of an infinity cosmos is you can actually do quite a lot with much less. So an infinity cosmos has a quotient that is a 2 category, a strict 2 category, not even a bicategory, whose objects are the infinity categories in the infinity cosmos. In other words, just the same objects as you had before. The one cells, the one-dimensional morphisms, are the infinity functors in the infinity cosmos. In other words, just the morphisms you had before. And now the 2 cells are something we're going to call infinity natural transformations. So what these technically are is they're homotopy classes of 1 simplices in the mapping quasi-categories. Essentially what we've done is we've replaced the Hom quasi-categories by their homotopy categories, and that converts from a simplicially enriched category into a 2 category. And what's surprising is that this quotienting operation is a reasonable thing to do. So it's a simple construction, but some evidence that we haven't forgotten too much information is the following theorem. So inside a 2 category, there's a standard notion of equivalence. So we would say objects in a 2 category are equivalent if there exist morphisms, one going from one to the other and one going from the other back to the one. So that when I compose them up, there exist invertible 2-dimensional morphisms connecting them to the identities. So here, this is an invertible 2-dimensional morphism from the identity to GF, and this is an invertible 2-dimensional morphism from the identity to F composed G. And this 2 categorical notion of equivalence, you can prove coincides exactly with the sort of native notion of equivalence in the infinity cosmos. And what that coincides with are like the weak equivalences in the model. So in other words, Riehl already told us what an equivalence of quasi-categories was. And in the infinity cosmos of quasi-categories, in the homotopy 2 category of that is in this quotient 2 category, it's just the 2 categorical equivalences. And similarly for all the other models. So what that means is that if we're working in this 2 category in kind of a non-evil way, meaning we're characterizing objects up to equivalence, we're doing something that's homotopically correct. So we're characterizing infinity categories up to equivalence, and that's kind of super, super important. Okay, so here's how the synthetic theory of infinity categories works. So again, there's an analytic theory of infinity categories where you would define an infinity category to be a quasi-category, and then you would define a limit to be like a particular vertex in some simplicial set, so that when you have these spheres in some other simplicial set, that they can be filled to simplices. That's analytic because I'm referring to the combinatorics of that particular model. Here's the synthetic definition. So an adjunction in between infinity categories is an absolute right lifting diagram in this homotopy 2 category. Similarly, a limit is an absolute right lifting diagram in this homotopy 2 category. So it's exactly the definitions I gave you before for ordinary categories. And now the proof that right adjoints preserve limits and left adjoints preserve colimits is the one given previously. So the same proof that works for ordinary categories using the 2 category of categories, functors, natural transformations works for infinity categories using these 2 categories of infinity categories, infinity functors, infinity natural transformations. You just sort of stick an infinity in front, but you use exactly the same proof. And this again is a pretty big surprise to people working in the field. So if you're familiar with another proof that right adjoints preserve limits between infinity categories, you might wonder where all the work went. Once the work here is in sort of learning what a 2 category is, but that's some work that you can do. And the more delicate task is that proving that these definitions are correct. So, the notion of a junction in a 2 category is, something we're just kind of taking off the shelf, and we're taking all of the theory of adjunctions on the shelf. It's very wonderful to work with. It's not at all evident that it's the same definition of a junction that Lurie gives in higher topos theory, for instance. But we prove that. There's an appendix in the book that takes care of that. And similarly, we show that our limits recover Riehl's definition of limits. So when we specialize these synthetic definitions to the infinity cosmos of quasi-categories, we have to check, and these checks are often a bit technical, that they recover the established definitions, which are analytic. But now that we've done that, you should feel free to start with the synthetic definition as opposed to the analytic one, because they are the same after all. Okay, so, well, let me stop and see if there are any more interruptions, and then we can or cannot continue either way.
Well, I do have a question. So what do the theorems that you prove synthetically for infinity cosmoi say about, things that form infinity cosmoi that are not models for infinity categories, like those n comma infinity categories and so on?
Great, wonderful question. I'm really happy you asked me that. It's not entirely clear. So, well, I guess in some cases it's sort of clear, and in other cases it's less clear. So, for instance, in infinity cosmoi whose objects are kind of fibered or parametrized infinity 1 categories, it's just kind of a parametrized version of limit and parametrized version of adjunction, and it's sort of the same as before. But it's more of a mystery in the higher dimensional examples. So in particular, there are infinity cosmoi whose objects are theta 2 spaces. So that's a model of infinity 2 categories, for instance, or twofold complete Siegel spaces. That's another example. And so what I think these are they're sort of slightly impoverished. So they're still true, but the question is like what the definitions are in that case. And an adjunction in this sense, interpreted in that setting, is kind of a slightly impoverished, in the sense of not fully general, notion of adjunction in infinity 2 category theory. So the ordinary 2 categorical notion of adjunction is a relevant adjunction to infinity 2 category theory, but not the most general one. There's this thing called a local adjunction that would be sort of even more general than this, and that's not captured here. And similarly, there are various different sorts of limits in infinity 2 category theory. You can ask that cones are sort of pseudo-commutative or maybe only lax commutative, and you can kind of weaken the universal properties. And this is telling us that certain slightly special adjunctions preserve certain slightly special limits, but it's not the fully general story in that context. So my sense is that if your goal is to develop infinity 2 category theory, for instance, or infinity n category theory, these theorems would start you off a little bit of the way, but there's a whole bunch else you'd have to do, which is to adapt the definitions to really cover the fully general notions in those settings. Another example is we have a theory of Cartesian fibrations that is really optimized to the infinity 1 case and doesn't capture the full notion in the higher contexts. So great, yeah, very good question.
Thank you. Well, thank you. Thank you.
So I guess very, very briefly, I'll just tell you a little bit about model independence. As I mentioned, we have these different infinity cosmoi, sort of one for each of the models of infinity categories. But thanks to the community who developed these models, we also have comparison functors between them. We call them cosmological biequivalences, biequivalence being borrowed from two category theory. That's the best notion of equivalence between two categories. And a way to understand the model independence theorem is that these biequivalences, in other words, these like change of model functors, preserve, reflect, and create infinity categorical properties and structures. So for instance, the existence of an adjoint to a functor, the existence of a limit to a diagram, the property of a given functor being a Cartesian fibration, the representability of modules between infinity categories, that module business, that's about like universal properties and the innate lemma and all that. The existence of pointwise Kahn extensions, these are the sort of questions you could ask in one model and answer in another. But what's really important is there's limits to the synthetic method, and it's certainly important to acknowledge that. So the definition of an infinity cosmos is really pretty sparse. It only axiomatizes the existence of limits and not any colimits. So there's some results in the theory of infinity one categories that you're just never going to be able to prove from those axioms because they're sort of not enough axioms, basically. And also there's all this literature that's been done already. I mean, part of the points is not to just go on forever reproving everybody else's theorems, but to just be able to use everybody else's theorems in a more general setting. So something that's very, very important is that even if the theorem is proven using a particular model, that its conclusion can be interpreted in other models. And that sort of thing is a little tiny bit delicate because even if we're going back to ordinary category theory, not every statement about categories is invariant under equivalence, kind of much less change of model. So when you start in one model, like complete Siegel spaces and pass to another Siegel categories and then come back, you're not likely to have an identical complete Siegel space to the one you started with, maybe only an equivalent one. And so you need, for this change of model stuff to preserve and reflect categorical statements, it needs to be invariant under equivalence between infinity categories. And, a statement like this infinity category has exactly one object is not the sort of statement that's invariant under equivalence of infinity categories. This is true for ordinary categories too. So it's kind of a well-known problem. So there's a sense in which like the traditional language for mathematics is like too permissive. It lets you make a bunch of nonsense statements. About the natural, there are various different constructions of the natural numbers in set theory, for instance. And in one of them, you can ask a sentence like, does 17 have 17 members? And for some models of n, that will be true. And for others, that will be false. And in all models, it's like nonsense. So you have to be a little bit careful with the formal language. So Michael Mackay has done a lot of work on this, and we're able to sort of take it off the shelf and develop a formal language for model-independent infinity category theory. So what he does is so it's a restricted form of ordinary first-order logic. That's like a syntax for expressing mathematically meaningful statements. And this can be adapted to the structure that we use to develop the formal theory of infinity categories in an infinity cosmos, and which is the homotopy 2 category that I was mentioning previously, but really an extension to something we call the virtual equipment of modules. That's allowing us to talk about universal properties as well as like categories and functors and natural transformations. And the theorem is that any formula or sentence about infinity categories that is written in this particular language of a virtual equipment, so that's some formal language, it's like first order logic, but it's more restrictive. Any statement that can be expressed in that way is invariant under change of model. So again, what this means in practice is we can look at somebody else's paper on infinity category theory. We can ignore the proofs. We have to assume the proofs are correct, of course. But then if you just look at the theorem statements, if that statement can be expressed in this formal language, then we know that the result must be true in all models. That's the upshot of this theorem. So I'm not describing it in more detail because the signature for that formal language is a bit complicated. So this is the fold signature for virtual equipment. That again is a subject for another talk, but I just wanted to mention that was there. All right, so here's the summary. So in the past, the theory of infinity categories has been developed analytically in a particular model. But a large part of that theory can be developed simultaneously in many models by working synthetically with infinity categories as objects in something we call an infinity cosmos. So the axioms are a little bit funny. They're chosen to simplify proofs by allowing us to work sort of strictly up to isomorphism insofar as possible. But you could certainly imagine tweaking the axioms in a number of ways, relaxing them so that there are even more examples of infinity cosmoi. And I think fundamentally that wouldn't change anything. So much of this development, in fact, takes place in the strict two category of infinity categories, infinity functors and infinity natural transformations. In both analytically and synthetically proven results transfer across change of model functors called biequivalences, and statements about infinity categories written in this formal language are model independent. So there's some references. Thanks so much. I really appreciate it.
Thank you very much, Emily, for the great talk. Thank you. Well, are there any questions or comments for Emily?
I mean, I have a bunch of questions, but I wanted to give other people a chance first. Hi, Emily.
Yeah.
So I had a question here. Just so the infinity cosmos is meant to be independent of models, but it's a category enriched in quasi-categories. So you're sort of favoring the quasi-categories right off the bat, right?
Yep, that's absolutely true, and everybody objects to that. So thank you for being that person.
I don't.
So you're right, absolutely. So we do use a model. So why do we do that? I mean, on the one hand, the fact that we're basing it off of quasi-categories is going to make it a little easier to compare the synthetic definitions with the analytic ones, which are typically expressed in the language of quasi-categories. So it's a little bit more useful for us from that point of view. Number two, I mean, we really did need a very precise definition of what an infinity two category was. And the, sort of strictest one that we were aware of is a category strictly enriched over simplicial sets in which those simplicial sets happen to be quasi-categories. So that was very convenient. Another thing to say, though, is once we've truncated to the homotopy 2 category, so when we're the proof that right adjoints preserve limits, for instance, doesn't take place in the full infinity cosmos, but in this quotient. And that quotient would be the same had we enriched over something else. So the purely two categorical aspects of the theory don't require this enrichment over quasi-categories, but there are some other things that we do use it for.
Okay, thank you.
Thank you, Bob. Are there any other questions or comments?
I wanted to ask about, so you're also involved in a different approach to synthetic theory of infinity categories inside homotopy type theory with Mike Schulman. I'm familiar with this approach. I even taught a course based on your book and it went great, but I'm not too familiar with the other approach. I know it involves adding stuff to homotopy type theory to capture shapes, which I guess is similar to this approach requiring things to be cotensored over simplicial sets. But could you, and I imagine that the other approach is sort of a little bit more, it forces you to be more invariant in your statements from right off the bat. But well, is that true? And can you just compare them in general?
Yeah, great. So thanks for that question. So what Omar's referring to is, I would summarize in the following sense, is that I hope that in 100 years, this book is totally obsolete, that this is not how we're thinking about infinity categories anymore. And the only way that seems reasonable or likely to happen to me is if we change our foundation system. So the reason it's so difficult to do infinity category theory is our traditional foundations of mathematics are based on set theory, and infinity categories just don't have a lot of sets involved. There's not really a well-defined set of objects. There's not really a well-defined space of morphisms. There's a well-defined homotopy type and not a well-defined space. So there's just like not a lot of sets in the notion. So if your rigorous definitions have to involve sets, then you're kind of doing something wrong. So what homotopy type theory refers to is that's a different foundation system where, some primitives are sets, but not all primitives are sets, sort of more exotic homotopy types are kind of equally the primitive notion. And a really, really wonderful feature of this new foundation system is that it collapses the distinction between contractibility and uniqueness. So to say that something has a unique element means in homotopy, so in the system homotopy type theory, it works just like uniqueness in ordinary math. So if something is a unique thing, then if you call it X and somebody else calls it Y, X is equal to Y, you know. But what it corresponds to semantically, how it would compare with set theory, is the notion of a contractible space. It's saying that the moduli space of all such whatever is contractible. And this happens all over the place in sort of homotopy coherent mathematics or infinity category theory. So there's a contractible space of composites, but not a unique composite. But again, in homotopy type theory, contractibility becomes uniqueness. So what I like about this formal system is I can actually define what an infinity category is, and it's a definition that actually makes sense. I mean, here we define an infinity category as an infinity cosmos, which is cute, but it kind of doesn't make sense. Whereas in that formal system, an infinity category, it's a type in which any composable pair of arrows has a unique composite, because unique now means contractible space, and that's good. And then any isomorphisms are equivalent to, or paths are equivalent to isomorphism. So there's a condition. So what's not so good about that formal system is homotopy type theory is still under development. And, you know, it's hard. We can't really do homotopy coherent mathematics and homotopy type theory right now. There's a problem in specifying an infinite homotopy coherent diagram. We don't really understand universes of infinity categories very well, and to get sophisticated examples of infinity categories, you know, to talk about Cartesian fibrations, you know, we really need to know more about universes. So, you know, I would love to, you know, kind of throw this book in the trash and work with that method instead, but we're kind of not there at present. So.
Right, but so you do expect these things to be possible. Like I don't know, it's always seemed to me like this even just defining a simplicial set or something like that, just anything that requires an infinite amount of coherence, it just seems very difficult there. And I haven't really kept up with things, so I don't know how close people are to solving that problem or any similar problem, but it just seemed very hard the last time I looked into it.
The problem that you're referring to is still very much open. A lot of people have worked on it, and we've made essentially no progress since the problem has been stated. So that's a reason for concern. There has been some progress made on the kind of background homotopy type theory system, though. You know, using like cubical homotopy type theory as opposed to book hot. And, you know, the move that Mike and I make in introducing these simplices in the context is kind of like that. You know, so I don't know. I mean, you have to be an optimist and hope things are going to work out. But there's a lot of very hard work that needs to be done to make that dream a reality, and it might not happen. So, which would be good for the book. Then the book is still relevant.
Right. Yeah. Thanks.
Sure.
Yeah. Thank you, Omar. Are there any other questions or comments? Well, if there are none, I do have a question.
Please.
Yeah, well, so is there, so I suppose this has something to do with Bob's question, well, or not, maybe not. So is there anything to be gained from considering infinity cosmoi were like a weakened version of infinity cosmoi? So infinity, so weakly enriched categories over quasi-categories, satisfying all the weaker versions of the completion conditions.
Yeah, absolutely. I mean, the thing to be gained is you should be able to include the models that I left out. So I threw out the relative categories model, for instance. That's a very nice model of infinity categories. It'd be nice to have it in. So I suspect, though I don't have a precise theorem statement in mind, that's kind of what you would gain. I mean, the cost, though, would be kind of replacing the homotopy 2 category by a bicategory.
Yeah, that's a trade-off. Yeah.
I mean, somehow they're the same, but somehow like a bicategory is a real pain. So
no, I would agree that's a big trade-off.
So I mean, Adam and I fought over it, and I I think the right perspective, though, is that this is a provisional definition, and if you want to use it in a paper and change it in some way, totally have our blessing. So,
Okay.
Mhm.
Okay. Okay. Yeah. Thank you.
sure.
Um,
I mean, in particular, I hope at some day there are variants that are tailored more towards these higher dimensional examples.
Yeah.
You know, that change the enrichment in particular to give kind of more refined higher dimensional information. So you could talk about the local adjunctions or whatever, but
Right.
yeah.
lax limits and co-limits.
Okay. Yeah. Well, just thank you, Emily. So there's a so what are single object infinity cosmoi? So, well, you obviously have a quasi category plus a bunch of things. What are those things?
I don't know.
Okay.
I have to think about that. Yeah, that's a fun question. I have no idea.
Well, it's not. Maybe
I mean,
there
you have
aren't.
to have all these
right?
limits, which would be a little weird.
Yeah, yeah. I'm guessing maybe that forces it to be terminal or something. Well, I'm not even sure.
Yeah, I
the
guess
answer.
that's a point. So if you have in fact, Omar's 100% right. So one of our axioms is that there exists a terminal infinity category.
Right. Yeah.
And so
Yeah,
that
yeah.
single object is terminal. So the Helm space is trivial.
Right.
So,
Okay.
so
Yeah.
good,
Okay.
good teamwork. So,
Well, well, you briefly mentioned isofibrations, and so well, I guess you already answered this question a little bit during the talk, but why are they so? Why are they like an essential ingredient for the definition? What is it about them that's so important?
great. So they're not an essential ingredient at all. However, they're a great convenience. And the reason is when we're proving a theorem or something like that, we're working with diagrams of infinity categories and functors, and our diagrams often commute strictly, like in the sense of one category theory. And that's kind of crazy in infinity world, when everything's sort of up to equivalence, like your diagram should never commute strictly. But the reason that our diagrams do commute strictly is because of the isofibrations. You can lift away any isomorphisms that inhabit a commutative square. So yeah, completely inessential in some sense, but also extremely convenient because we have strictly commuting diagrams, and then we can appeal to these strict universal properties to induce maps and stuff. So,
Okay.
so we're like using one category theory essentially to do infinity category.
Yeah.
Right.
Yeah.
And yeah.
Okay. Yeah. Well, I think that's.
I wanted to ask one more thing. I think I've already asked you this before, but maybe the answer has changed. So I think that for me, like the first thing missing from your book with Dom is monoidal structures.
Mm-hmm.
And it feels like, at least for, like just monoidal or symmetric monoidal, it should be easy to add in by just, this, including like an object that plays the role of finite of delta or of finite pointed sets and asking for fibrations over it or something like that. And so maybe En monoidal, which I also care about, is harder to fit in, but at least like E1 and E infinity should be easy. Has anybody written something along those lines, or?
Yeah, no, not that I'm aware of. So that's open. I would, if a student wants to work on that, I'd be happy to be consulted, and I'd love for somebody to get that done. So
right. Okay. Yeah. Thanks.
Sure.
Yeah, that was a really nice question. Yeah, well, I think so. Are there any other questions or comments for Emily? We don't want to keep you forever here.
Yeah.
Well, if not, let's thank Emily